So in this podcast, we're going to be mostly focusing on getting to these solubility graphs that you see here on page 6. But we need to talk about a couple of words first and some situations on page 5 before we can get to it. So let's jump right in. We've talked about solubility already, mostly in when we defined the word soluble and insoluble, telling us, well, will it dissolve or will it not dissolve? So solubility is very much related to those words. Solubility is generally regarded as the amount of solute required to produce a saturated solution. And so that's how much will dissolve in that solution. Sometimes this is just kind of referred to as the generic ability to be dissolved, kind of coming back to that, yes, will it or won't it, soluble or insoluble. But it can describe a specific number, how much will fit, how much will dissolve. And that's where the rest of these words come from. You notice that saturated solution. Saturated solutions are kind of solutions that are full of solute. They contain the maximum amount of solute that they possibly can. So think of the word saturated as the word full. It's probably not a word you use a whole lot around, but you could use it to describe other things that are full. Like if you are washing dishes and you squeeze the sponge underneath the water and release it, it's going to soak up as much water as it possibly can, and it's going to become saturated with water. So naturally from there, these other words make a little bit more sense. Unsaturated, if saturated is full, unsaturated is just unfull or not full. So unsaturated solutions contain less than the maximum amount of solute. And then a supersaturated solution, if saturated is full, then that is a super full solution. And these solutions contain more than the maximum amount of solute. So this is kind of, like I said, it's kind of like thinking of something as full. And just like you eating food at the dinner table, you're going to stop when you're full. And of course, everyone's fill level is a little bit different, but whatever is full for you, you stop when you reach there. Super saturated solutions that are super full, that have gone beyond what they would normally be able to be dissolved, are not something that's just going to happen on their own. That's not just putting a little extra in and a little extra dissolves. You have to do something special to the solution to force it to take more than should be dissolved. So we'll talk about those in a little bit more detail in class together, but that's not just something that just happens all on its own. So one of the things that you will often be asked about these solutions, or that we can use in order to identify what type of solution we have in front of us in the lab, is by adding a little bitty crystal of the solute that we've been using to dissolve and make that solution. If we add a little single crystal to that solution, then that solution is going to act in a certain way, and it's going to help us figure out whether or not it was full, whether or not it was saturated. And once again, this kind of comes back, the solution is going to act a whole lot like a person would act with their full or not, and you offer them just a little bit more food. Think about a saturated solution. If that solution is full, if that person is full, and you offer it another little piece of food, they're going to say, no, thank you, I'm full. So if we put a crystal into a saturated solution, the solution's going to say, nah, I'm full. I'm not going to dissolve that crystal. And it'll just sink to the bottom, and it'll sit there, and it will not dissolve. On the other hand, if we have an unsaturated solution, an unfull person, they're still hungry, you offer them some food, they're going to say, yes, please, and they're going to gobble it right up. Well, a solution will do the same. If you put a crystal into an unsaturated solution, it's going to dissolve and go into that solution and become part of the solution instead of sitting there separately. Now, with this supersaturated solution, if you have somehow managed to shove in some extra food, like you got to that full level and you were saying, okay, I'm pleasantly full. Maybe this is Thanksgiving though. And your aunt comes around and is like, oh, we just have a little bit more food. We really want to finish it off. And you're like, okay. And she forced you to dissolve more, to eat more food. And that's already happened. And then dessert comes around, and she forces one last more thing into your stomach, and you're already feeling so overfull. That one last little thing might just overdo it for you, and that might result in that food and maybe some of the other food that you've eaten coming back out of your stomach if you were really that unstable and that over full already. And the same thing will happen with a solution. It's just not quite as messy. If we add a crystal to a super saturated solution, then that crystal, let alone, won't dissolve. And all of the extra solute, all that stuff that we said is over our full level, over our normal kind of saturated level, all of that extra stuff will come back out of solution and recrystallize into a solid and not be dissolved anymore. So the solution is kind of throwing up all of its extra crystals. And that's actually the way that we make rock candy. We make a supersaturated solution, then you roll the string into some sugar crystals, and put it into that supersaturated solution, and then those solutions, the solute, will recrystallize on that string or stick or whatever you used, and then you got rock candy. So, pretty simple stuff, and kind of acts like people act. It kind of makes sense here. But these are some important words to know, and you will definitely see a question about them on your test in the future. So now let's talk about some related words before we move into those graphs on the next page. The word dilute or diluted means that we have a very small amount of solute in the solution. It's just a little bit of stuff in a lot of bit of water. Concentrated, on the other hand, is a large amount of solute in a solution, or a lot of solute with less solvent, less overall solution volume. And so a lot of people start to think that when we talk about things being saturated, that they think that it's the same thing as concentrated. But saturated means full. And so you can be saturated and dilute. It's just that the solution is going to be full with a small amount of solute. Dilute just means a small amount of solute. So there could be some solutions, and we're going to see a little bit more about this on the next page, that are full, that are saturated with less stuff than other solutions would be full at. These last two words, miscible and immiscible, are kind of related to soluble and insoluble, but this tends to be talking about liquids that will kind of dissolve in each other or be soluble in each other. And immiscible liquids are liquids that are not soluble in each other. So it's basically soluble and insoluble, but it's for liquids. You wouldn't actually see a solid still left over if it's insoluble. It'd just be not mixing together like oil and water. So we've already talked about how temperature can affect solubility just a little bit at the bottom of that page in our notes where we talked about factors that affect solubility. Well, temperature in general will increase the solubility of our substances, but really that's only true for solids. Solids are going to have an increased solubility at higher temperatures. So heat it up, you're going to be able to dissolve more sugar or salt. But the solubility of gases actually decreases as our temperature increases. And this kind of makes sense because with solids, remember we have these three states of matter, solids, liquids, and gases. And the more energy you add to a solid, it will turn into a liquid. It'll melt. The more energy you add to a liquid, the more it'll turn into a gas. So when we add heat to a solution with a solid in it, that makes the solid want to become more like a liquid and makes it easier to mix in with that liquid. On the other hand, when we have a gas that we're trying to get dissolved into a liquid, we need to cool it down a little bit so that it'll act more like a liquid and want to mix with that liquid. If we heat it up, then that's going to tend to make that gas come out of the liquid, tend to want to be more of a separate gas all on its own. And so think of this like a soda. It's going to be more fizzy, and you're going to taste more of that carbonation when it's cold. When you have a warm soda, it almost tastes like it's partially flat, especially if you leave it open and warm. Then it's going to get flat really quick. It's going to lose all of the gas that was dissolved in your soda liquid. And that is in part why some fish like to sit at the bottom of lakes and ponds on really hot summer days. It's because deeper in the lake, it's cooler, and that cooler water actually has more dissolved oxygen, and so it's easier for the fish to breathe without having to do as much work to get around get the oxygen that they need. So it's more efficient. So we are going to be looking at these solubility graphs, and you can actually see some of these same things about gases and solids increasing and decreasing solubility right here on it, because any of these lines with a negative slope that are going to decrease how much they can dissolve when we go to those higher temperatures are going to be gases. The things that have a positive slope that increase their solubility over time as we increase that temperature are the ones that are solids. So we can see that happening here in front of us, but there's a whole lot more that we can pull out of these solubility curves. And it tells you in your notes there that these lines represent the maximum solubility level of substances at different temperatures. So we got lots of different lines, lots of different substances, and this kind of reinforces that idea that I was talking about on the last page, that different substances are going to be saturated at different levels. So some of these down here at the bottom that are saturated at very low levels are still going to be a very dilute solution, even though they're saturated and full. So let's look at a couple other key things inside this graph. First off, the amount of solute that's being dissolved is here on our y-axis. It says grams of solute. On our x-axis, as I already pointed out, we have our temperature. So the amount of solute that's going to be dissolved depends on what temperature that we're at. And if we look and we see all these different lines, the different substances have different lines, which means they have different solubility levels, and that line represents saturated. Anything below that line for that substance would be unsaturated. Think of that as under our saturated line. It's unsaturated. Over the line is going to be oversaturated or supersaturated. So we're going to be talking about that as we go through. And then this graph that we have here is for solutions made with 100 grams of water. And you'll notice that's the other part of what's written here on our y-axis. With the amount of solute that dissolved, they also specified an amount of water. And that's important because, of course, if we had more water, we could dissolve more stuff. An ocean can dissolve more salt than a cup of water can. So it's important that we define the amount of water in the graph so that we can kind of reflect on that, especially if we have a different amount of water. That's going to become important. So let's go ahead and go through a couple example problems. We're going to work some more on these in class and do some practice on the next couple of pages, but there's a lot of different questions we can ask you about this graph, and it really just comes down to learning to read the graph and figuring out how to get the information off the graph and understand it. So here in this first question, it's asking us what is the solubility of a saturated solution of KNO3 at 10 degrees Celsius. So the important thing is to kind of pull out what substance we're dealing with, because that's going to tell us what line we are looking at on our curve. And then also notice that it gave us a temperature. If they give us a temperature here, making sure that we're looking at the 10 that's on the x-axis for that 10 degrees Celsius, not 10 grams, we basically just need to bring them together. So I'm going to follow that 10 degrees up to where it hits our KNO3 line and follow it over to the y-axis, and that will tell me how much stuff will dissolve. That'll tell me the solubility of our KNO3 solution. And that's just a little bit above 20. I know some of y'all might say it's 21, but personally I think that's 22, and I almost put degrees Celsius there. It's important that was a grams number on that y-axis there. So 22 grams should dissolve. Quick, easy thing, just putting together the information that they had in this problem. This next problem asks us what compound is saturated if 80 grams of that substance, whatever it is dissolved in 100 grams of water at 50 degrees Celsius. So we've got three numbers here. But first and foremost, if it tells us that we have 100 grams of water, remember, this graph is made and designed to answer questions about 100 grams of water. So that just kind of checks a box in our brains, and we can ignore that number from here on out in that problem. It's only if it's a different amount, if it's not 100 grams of water, that we have to do something with that. So let's focus on that 80 grams and 50 degrees Celsius. Well, 80 grams is here on the y-axis, 50 degrees Celsius is here on the x-axis. My instincts tell me, let's find where they meet. And if we follow them up together, then they meet right here at this x. And hey, that happens to fall right on my KNO3 line. So what compound is saturated? Which compound is full with that 80 grams and 50 degrees Celsius? Well, that's going to be KNO3. And now, in question 3, we have a solution of sodium nitrate containing 140 grams in 100 milliliters of water at 65 degrees Celsius. Even though this is 100 milliliters of water, for water, milliliters and grams are the same thing. Its density is 1 gram per milliliter. So once again, I can ignore that 100 of water and focus on the 140 and the 65. And I also should probably find my sodium nitrate line. It's right here by the potassium nitrate line. And let's go ahead and find that 140 grams, and 65 is going to be right here between the 60 and the 70. And if we follow those up to where they meet, and we'll put an X there, we need to basically ask ourselves, it's asking us, are we saturated, unsaturated, or supersaturated? But remember, the line that we have here is full. The line is saturated. Am I on the line? No. So that means that I'm definitely not saturated. And so at this point, I'm asking myself, am I unsaturated or oversaturated? Unsaturated or supersaturated, under or over the line. And if we look up and down at that line, my X is above the line. So the situation in the problem with these numbers is over the saturated level, which means that this is a supersaturated solution. If that X had been under the line, then that would have been unsaturated. You need to look just vertical, not left and right, just up and down for over or under, super or unsaturated. But not too bad, I hope. This next question asks us which substance has solubility changes the least from 0 to 100. So if our solubility is on that y-axis, we want to look for the line that changes the least on the y-axis. And it's kind of hard to see it here, almost because it blends in. It's so close to that 40 grams line. But that, in my opinion, would be NaCl, at least on this graph. And then question 5 asks us, at what temperature would a solution containing 40 grams of KNO3 in 50 grams of water be saturated? So this one is giving us information about the KNO3 line. And it's giving me an amount of grams, and it's asking me at what temperature that would happen at. So we are going to be following a number over from our y-axis to our graph and then down. But if you notice, this says that we're doing this in 50 grams of water. My graph is not designed for 50 grams of water. It's designed for 100. And that's standard, but sometimes we don't make solutions in 100 grams of water. So what we need to do is make our information match the graph so that we can use this graph in order to answer this question. So we just need to make this question talk about 100 grams of water. What do we need to do with our amount of water to get it to 100 grams? Well, we need to multiply it by 2, and that would now be 100 grams of water. Well, if we want to keep the solution kind of relatively the same, not make it more dilute or more concentrated, if I multiply the amount of water by 2, I also need to multiply the amount of stuff I'm dissolving in it by 2. So what I need to be looking for on this graph is where 80 grams hits our KNO3 line, because 80 grams in 100 grams of water is the same relative concentration as that 40 grams in 50 grams of water. So we're going to follow the 80 over to that KNO3 line, and that matches up basically perfectly at 50 degrees Celsius. So that is our answer. We're not doing any more math with that temperature once we get it. We only do math, we only multiply and divide our grams. so that we can use that graph to find that temperature. So just a couple more types of problems here that we need to practice. So in number 6, this seems a little bit more complicated, but it really is a simple kind of two-step problem that we're going to work with if we understand what's going on here with this solution. This says we have a saturated solution of KCl in 100 grams of water. So good, our 100 grams of water is the same. Let's find our KCl line. And it says it's cooled, or it's at 100 degrees Celsius when it's saturated, and then it's cooled down to 20 degrees Celsius, and it asks us how many grams of KCl will recrystallize. So we are going to be following these temperatures, this 100 and this 20, up to our KCl line in order to find 2 different grams. And what it's told us is that this is saturated and filled with solute at that 100 degrees Celsius. And that's where about 55 grams will dissolve. And then we cool it down. And evidently, some of this stuff is not going to stay dissolved at that lower temperature. We dissolved more at the higher temperature than will fit at that lower temperature. So what we need to do here is find the difference, just like what we talked about with that super saturated solution. Adding a little crystal will make that extra stuff come out. Well, after we cool this down, any of the extra stuff that couldn't stay dissolved at that lower temperature will come out. So we're going to need to subtract those 2 numbers. And we'll take that 55 grams and subtract that 32 grams. And evidently I disagreed with myself. And like I said before, that it's a little bit different, and 1 or 2 grams is not a big deal as long as it's in that same relative area, low on the 30s. If you said 35 or 37, we would be losing some points there. But 31, 32, basically the same difference. And the most important part is that that's going to end up being around 23. But once again, I'll allow for that little variation in each of those numbers if we've got it, so that we can get that correct answer out at the end. So don't worry too much on whether it's exactly 31 or 32. Just make sure you're doing the right general things with those numbers. And so this last question, how much sodium nitrate must be added to make a saturated solution in 50 grams of water at 10 degrees Celsius? So we've got a weird amount of water, and then we're trying to figure out how much of our sodium nitrate has to be added to make that. Well, this is information we're going to be pulling off of the graph. And before, when we were looking at the graph with a weird amount of water, we had to multiply our numbers before looking at the graph. But here, the numbers that we have about our solution is temperature. And we don't multiply temperature. I guess way to think of this, if I have twice as much of a solution at a specific temperature, the temperature isn't doubled. Temperature is not going to change when the amount of substance changes. Remember, we called those intensive properties. So never multiply or divide your temperatures. So if I can't multiply or divide anything yet, I'm just going to go and look at that 10 degrees Celsius and follow it up to our sodium nitrate line. And that lines up basically at 80. So what this tells us on this graph is that 80 grams of sodium nitrate will dissolve if I had 100 grams of water. But now that I have grams, I realize that I haven't really answered my question, because this is 50 grams of water and 80 grams. So if I have that information, then I need to turn it into the answer for my problem. What do I need to do to 100 grams to turn it into 50? I divide by 2. So I'd have to do the same thing with my grams of my solute, which means that'll be 40 grams in 50 grams of water.